Hey everyone, welcome to today's Explainer, and a big welcome to all you focus learners out there joining us. Today, we're unpacking a real piece of everyday magic. Have you ever marveled at how your devices just seem to finish your sentences before you even finish your thoughts? Well, let's demystify the lightning-fast data structure that makes that possible. All right, let's jump right into part one, the magic of autocomplete. So, autocomplete. It's a feature we literally use dozens, maybe hundreds of times a day. But have you ever stopped to think about how it actually works? Picture this. You're typing a search query. You hit I, then N, then T. And boom, instantly a menu drops down suggesting internet, interest, or international. How on earth does your phone sift through an entire dictionary to guess exactly what you're thinking in a fraction of a millisecond? Well, the secret isn't magic, right? It's just brilliant data structuring. See, the system takes the exact input characters you type and traverses them to instantly retrieve possible words based on that specific prefix. Instead of reading through a giant unsorted list from A to Z every single time you tap a key, which would take way too long, the system walks down a highly organized preset path. But to pull that off, the underlying data has to be stored in a very, very specific way. Which brings us to part two, meet the prefix tree. Say hello to the trie. Now, it's often pronounced trie, though it comes from the word retrieval. It's also known as a prefix tree. This specialized tree-like data structure really has one main superpower. It efficiently stores strings of characters by taking advantage of shared prefixes. That concept right there, shared prefixes, that's the absolute core intuition making this all work. Rather than storing every single word as an isolated island, a trie groups common starting letters together. And this brilliantly illustrates the difference. Let's say we wanted to store the words internet and interface. We'd literally have to store every single letter for both words, just wasting a ton of space. But by using a shared prefix, that's where the magic happens. Both of these words start with I-N-T-E-R. A trie recognizes this, maps out inter just one time, and reuses those nodes. It drastically minimizes redundancy. It is just an incredibly elegant way to save space and speed up your searches. Let's actually walk through how this branching works, node by node. Step 1. The system creates a path of shared nodes for I, then N, then T, E, and R. They share that exact sequence. Step 2. Right after that R, the tree splits. If you type an N, you travel down one branch that continues spelling out internet. But in step 3, if you were to type an F after the R instead, well, you branch down a completely different path toward the word interface. You're literally navigating the branches of a tree with every single keystroke. Moving on to part 3, anatomy of a tree node. Now, what's really fascinating here is how simple the building blocks actually are. Every single tree node has just two fundamental attributes. First up, it has children, basically a map giving directions to the next possible letters. Second, an end-of-word indicator. This is just a flag that tells the system, hey, the sequence of letters ending right here, that makes a valid complete dictionary word. Let's look a little closer at that first attribute, the children. How exactly does a node store references to the next letters? Well, you've got two common options. You can use a hash map linking a character key directly to a child node value. This gives you maximum flexibility. Or if you know you're only dealing with, say, the 26 lowercase English letters, you can just use a fixed array of size 26. An array is incredibly fast and memory efficient when you know your character set is strictly limited. So, what about that second attribute, the end-of-word indicator? We can handle this in a couple ways. You could use a simple Boolean attribute, just a true or false flag called isWord. If it's true, boom, you found a complete word. Alternatively, you can use a string variable that stores the actual word itself right there at the node. You'd want to use this approach if your system needs to instantly grab the full, specific word rather than just confirming it exists. All right, let's zoom out a bit for part 4, built for speed. Let's see how this all comes together to build a complete web of data. In a fully populated tree, say one storing words like bite, bites, dog, and dig, all of those unique strings originate from a single empty root trinode at the very top. This root node doesn't actually represent any character at all. It's simply the starting line. From that blank slate, you branch out into the first letter of every possible word in your entire dataset. So the crucial point we need to look at is the time complexity. Whether you're inserting a word, searching for a complete word, searching for a prefix, or deleting a word, do you notice anything similar here? Every single operation is big O of K. The complexity is completely uniform across the board. But What does big O of K actually mean for our performance? Well, K simply stands for the length of the word you're dealing with. And guys, that is stunningly fast. It means the time it takes to search for a word has absolutely nothing to do with how many thousands or even millions of words are stored in the tree. It only depends on the number of characters in the word you are typing. If you type a 5-letter word, it takes exactly 5 steps to find it. Period. That right there is the secret engine behind instant autocomplete. Let's wrap things up with part 5, when to use tries. There are 3 primary real-world scenarios where this data structure absolutely shines. First, efficient prefix searches. If an engineering problem asks you to find all strings sharing a common prefix, a trie is going to be your best friend. Second, fast word validation. Think of spell checkers. If you need to quickly verify if a word exists within a massive set, a trie is perfect for that. And third, optimizing data storage. By reducing redundancy through those shared prefixes we talked about, tries let you store massive vocabularies without chewing up all your memory. We've journeyed from the everyday convenience of autocomplete all the way down to the Boolean flags inside individual nodes. But I want to leave you with this one thought to ponder. If a single trie data structure makes the search bar on your personal phone feel completely instantaneous, how massive, complex, and deeply branched do you think the trees powering the search engines of the entire internet really are? Think about that the next time you type a single letter into your browser. Keep learning, stay focused, and I'll catch you on the next explainer.